Hey there, everybody. Welcome to another Chem Complete lecture. And in today's episode, we are going to be solving another unknown in organic chemistry using various spectroscopy. So if you've been following along, we have been using degrees of unsaturation calculations coupled with mass spec, IR, and then the NMRs, including both carbon-13 and proton NMR. So that's what we're going to do here. We've got another unknown. So let's go ahead and get started with this. The first thing we want to do is check out the degrees of unsaturation. So the formula we have here is C5H9N. And if we plug that into our formula for degrees of unsaturation, we would have 2 times the number of carbons, which is 5 here, plus 2, plus 1. Now that plus 1 comes from the nitrogen because you always add 1 to your tally when you have a nitrogen. You would subtract 1 if it was a halogen. And then it's minus 9 because you want to subtract the total number of hydrogens present divided by 2. And that should give us the degrees of unsaturation. So that comes out to 4 when we calculate it. And then when we get 4 and divide that by 2, we end up with 2 degrees of unsaturation. And if any step here doesn't make sense, if you check the description below, I will leave a link to the online course. I have a completely free online course on YouTube that goes through each of the steps. So there's a lecture on degrees of unsaturation, a lecture on mass spec, etc. So if you're lost at any point here, I encourage you to just go through that playlist and teach yourself how to do these because they're not too hard once you get the hang of it. All right, so 2 degrees of unsaturation. That means we do not have an aromatic ring because you need a minimum of 4 for that. So anything suggesting an aromatic ring should be out. We could have a triple bond, we could have 2 double bonds, 2 rings, a ring and a double bond, things of that nature. So now we want to take a look at the mass spec a little more carefully since we have our degrees of unsaturation. So the M plus peak, the parent peak there, is 83 as the mass. So we're dealing with something that has a molar mass of 83. And what's interesting here is the most prominent peak, or what's called the base peak, is at 82. So that would imply the loss of a hydrogen or a proton. And usually if the base peak, meaning the most stable ion that's coming off of this mass spec, is just the loss of a hydrogen, this probably means we have a fairly acidic hydrogen. Now we don't know if that's due to a carboxylic acid or some other type of functional group, but we have a proton that's most likely going to be pretty acidic and can be removed pretty readily. Maybe there's some resonance stability or something like that. All right. Now, the other peak we see here that's fairly prominent is 55. And with 55, if you take 83 minus 55, you end up with 28. So a loss of 28, what could be a mass of 28? If you go through and you look at common mass fragments, one of the common ones for 28 is CO. So it's a carboxyl group, a C double bond O. Now that's not possible in this case because we don't have an oxygen in the molecular formula. We only have C5H9N. So without an oxygen, this is not plausible. And that really leaves the question what this is. So let's try to gather some evidence from somewhere else. We have an acidic proton and 2 degrees of unsaturation. So let's go ahead and move forward to the IR, which is actually at the top here above the mass spec. So when we take a look at the IR, there's 2 really important peaks here. The first one is 3295. So at the 3295 inverted centimeter, that wave number is correlating to something that is north of 3000, and that usually means it's going to be a hydrogen attached to a carbon, and that carbon is going to be involved in some sort of a pi bond. It's usually sp2 or sp hybridized. Okay, and around the 3300 region, you can have aromatic, but a lot of times it's going to be a alkyne, so a terminal alkyne, and this would also make sense because that proton there is mildly acidic. It's not super acidic, but it certainly could be removed, and you could have a resonance stabilized ion that's occurring there. So that would make sense. Okay, now what backs this up further, and what's even more important, is if we had a carbon-carbon triple bond, we should have some vibrational evidence in the IR that is pointing to that, and indeed we do. So at 2114, this right here, you see a very tiny but sharp, narrow peak. And that peak is going to correlate. The only thing in that region is a triple bond. So it could either be a carbon-carbon triple bond or a carbon-nitrogen triple bond. Now we do have a nitrogen, so it is possible that we could have some sort of a compound like that. Okay. Now, one of the other things that's important to consider here is, while this is not broad like an alcohol would be, it is possible this could also be an NH2 group, okay? Because we do see two distinct peaks. The first one's very tiny up here, and the second one is more prominent down here. But we could have a NH2 group of some sort. Now, the question here is going to be whether this NH2 group is present in or confirmed by the Proton Nmr, because we don't use IR exclusively to confirm that sort of stuff. Okay, so it is possible that we have a nitrile group. It's also possible that we could have an amine group with an NH2. So we need to carry on then and continue to look at the carbon-13 at this point. Now, we have two carbon-13s. We have the dept NMR, and we also have the proton decoupled, your regular C13. And we're going to ignore this solvent peak here. We don't count the solvent peaks when we do this. Now, something that's interesting, the dept, remember, that shows CH2s or methylene groups as inverted peaks. So you can see here we've already got 1, 2, 3 inverted peaks. So we have a minimum of 3 CH2 groups that are present in this compound. Now, the only other thing that we see here in the dept is this one that's further up on the chart here. Now, if you go down and you look at the regular C13, not the dept, you can see where it aligns. So this is a CH2, this is a CH2, this is a CH2, and then there are 2 peaks left here. Okay? One of them appears at the top in the dept. So that means that this is either a CH3 or a CH, and it would most likely be a CH if it's around 70 ppm, because that's very far downfield to be considered something like a CH3. It's not impossible, but it's most likely that it's a CH. All right. And then what we also have is, if you take a look right here, this is probably going to be some version of a quaternary carbon, because it does not appear in the dept. It's missing up here. And what we know about dept is that in the dept, anything that is a quaternary carbon, meaning a carbon attached to 4 other groups that don't have hydrogens, those are going to disappear in the dept. So this again makes the case for, if I have some sort of R group here, and then I have a triple bond carbon, right? The CH group is accounted for, and then a carbon that has no hydrogens and would be quaternary is also accounted for. And in this 70 to, let's say, 90 ppm region, that's an acceptable area for these alkane carbon-carbon triple bonds to appear in. All right, so what we have here now is a bunch of CH2s, and we also have most likely the making of this alkyne here. So when we put all this together, we could suggest something such as CH2, 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 and then the alkyne is on one end, most likely terminal from all the evidence we've seen, and then there's something else over here because we can't terminate with the CH2 on the left side of that chain. So now might be a good point to go back and check the degrees of unsaturation and the formula to make sure we're lining up and see what's left. So first of all, are we in violation of the degrees of unsaturation? So far, no, because if we have a carbon-carbon triple bond, that would take up both degrees of unsaturation. So we're within the realm as long as we're not adding any rings or double bonds going forward. So now, if we count up the 3 CH2s and the alkyne, the number of carbons would be 1, 2, 3, 4, 5. So that accounts for all 5 carbons. the number of hydrogens would be 2, 4, 6, 7. So that would account for 7 of the 9 hydrogens. So if we have C5H9N and we get rid of all 5 for the carbons, we get rid of 7 of the hydrogens. That would just leave 2 hydrogens and a nitrogen. Well, we did say that there was the possibility of having some sort of an amine group, and the only plausible place to put this amine at this point would be where this question mark is on the structure. So we would have a primary amine that's hanging out on the opposite end here. So this makes sense. We could probably call that and make a pretty good case for it right here, but we certainly want to go ahead and take a look at the proton NMR just to confirm. So the next thing we do is look at the proton NMR ppms. All right, now with the proton NMR, the first thing that I would call your attention to, and this right here is just a blow up of this region so that you can see it more clearly. So the first thing we have for the proton is right around, I'm going to say the 1.2 ppm area. We have a peak that is a singlet and it integrates to 2 hydrogens. So the 2 hydrogens that are there, if you take a note here, it says exchanges with D2O. That means that these are hydrogens involved in hydrogen bonding that readily exchange with water. So that would most likely make the case for an NH2 group. All right, and then if we take a look, we have 3 sets of CH2s, all confirmed right here. Now you can look at the different splitting patterns. So one of them is a triplet. One of them is a quintet, and then we have another one that's a multiplet of multiplets here. It looks like it's a triplet of doublets, okay? And then we finally have this 1H here. That would be the terminal alkyne that we're looking at with that H. So all of these line up and match, all right? The splitting here can get a little hairy when we have all of the CH2s, but if we take a look and we say, all right, I've got an NH2 and a CH2, a CH2, another CH2, right, and then the alkyne. So if you take a look at this NH2, that would certainly have the electron withdrawing effects that are going to be seen in terms of de-shielding. And so it would make sense that this CH2 that I'm putting a square around right here correlates to this CH2 right here. And the neighboring CH2 would split it into a triplet. So then this CH2, that's the furthest away from any of the groups because it's in the middle, so it sort of is centered away from the NH2, it's also centered away from the carbon-carbon triple bond. That one we would find right here. So we can see that that one has 5 peaks, and that's due to a CH2 on each side. So a total of 4, and we use the n+1 rule, that becomes 5. So all of the evidence here is coming together to confirm that the official structure that we want to propose, one more time, is we have the amine, it's a CH2, 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 and then we have a opposite end that has a carbon-carbon triple bond that terminates with that acidic proton. All right, so this is the structure that we can confirm. Hopefully everybody found this useful. We have a whole bunch of these on the channel, so this should be one in a playlist. If you want to see some others solved, you can go ahead and walk back through and find some of those. I'll be posting more as I have time. Again, down in the description, there will be a link for the entire free training course. And if you found this helpful, you can support the channel by going to chemcomplete.com. We have guides available. I have written an entire, I think it's like 40+ page guide on how to solve these. I break it down step by step. I have examples. I have tables. We talk about every important type of peak. We talk about the mass spec and break down the different fragments that you might see. So if you're interested in that, that will also be down below in the description. You guys can support the channel for a couple of bucks and you'll get that entire practice set that comes with it, along with just as much information as you can handle in terms of learning how to solve these problems. So as always, thank you for learning with us. Remember to like and comment. Anytime you can interact, it helps the channel grow. And I will see everybody in the next lesson. Take care, guys.